Welcome again to this new lecture about build system. So without further ado, let's get started with the presentation. So today we're going to see build systems. That is going to be the foundation that you will need. It's a basic technique that you will need in order to build your C++ program. So this is one of the most important lectures, if not the most important lectures we are going to give you during this course. Build systems are basically a tool that will allow you to build any C++ program. And at the beginning, it's a bit hard to get used to it, but with some experience, it just gets easier and easier over time. So believe me, stick with me. It might look complicated, but this is something you need to understand, and it's a tool you need to use in order to build any C++ program. So build systems somehow rely on something I like to call the software development ecosystem. That is basically all the tools related to software development. So most of the times when we think about writing software, what we like to think it's about the source code. That is the program that you want to write. That is basically the center of this picture. But there's also a lot of other stuff related that is basically satellite tools to this software development or this source code. So the one we're going to see today is basically build system. That is a tool that will allow you to build your programs. There's many other tools around software development, like the text editor, that is the one you use to write your code, some linters that can lint through your code and tell you some errors you might have in the future, the toolchain you're using depending on the target system, for example, which operating system you are using to develop your software, packages, for example, the debugger, that we might have a tutorial in the future about this, the continuous iterations and continuous development. That is something that will allow you to test your software on a web service platform to make sure that everything is working, formatting tools, and so on. So basically, these are some of the tools you might use when you're writing software. It's not the most important foundation for writing software to know the tools, but in order to write proper software, you need to use the tools. And one of those tools is build systems, and it's one of the most important because if you cannot build your C++ program, then there's no chance you will get to run your C++ code. So as we say on the last lecture, C++ is a compile language, and I will try to repeat this on every lecture, but I might forget, so I apologize in advance, and therefore we need to somehow build our program. So let's jump directly into the compilation process. So what is a compiler? As we discussed in the last lecture, it's basically another program. So we say, let's create this compiler, this translator, to translate our C++ code into something that the computer understands. So basically, the C++ compiler is in charge of transforming your horrible C++ code into binary format. So something that the computer can actually understand and execute. Binary code is basically this language that the computer understands, that is basically in forms of zeros and ones, but it's basically in terms of high voltages and low voltages, for those who knows what we're talking about. This is basically a really simplified diagram of a compiler, where basically we see here that we have our source code on the left, and then we invoke the compiler, or we call the compiler, meaning that we will pass to the standard input of this other program, that is a compiler, this source code. And this compiler will give us some binary code, some binary format data that we can execute in our processor. That this could be, for example, my laptop I'm using right now to record this lecture. So far on the Hello World example, we did this really simple compilation process that was basically invoking the C++ compiler and just specifying through the standard input which file you want to compile. This will be the program, and then it will give you an executable file that is called a.out, and it's ready to run. So far, no surprises. But the question would be, will it be always that easy? This somehow already sounds way too simplified. And sadly, the answer is no. And then all this tough stuff you will need to do, you are going to learn during this course, and especially on the first homework assignment. So this build system lecture is so important that there's one dedicated homework that goes within this lecture. So after you finish this lecture, you're ready to do this homework. And this is actually the first homework and the first important lecture we will give you, because if you don't know how to build the programs, then the rest is something you cannot even look into it. So pay attention, please, and then make sure you learn and you understand how this works. So every time you compile some program, behind the scenes, there's always 4 steps running. The first one is something that we got from C, that is to pre-process the source file. That is, for example, when we were talking about including some header file, then the pre-process will be in charge of doing this, and then it will basically copy-paste text around files. So this doesn't check anything in particular, but it's basically pre-processing your programs. Then the second step is going to be to compile it. This is somehow confusing or misleading, because traditionally we say compiler program to everything. But believe me that when I say compiler program, I basically mean to build a program following these 4 steps and not just the compile. But the compilation, technically speaking, the compilation process is going to take this C++ code that has been already pre-processed, and then it's going to produce some assembly code. This depends strictly on the target processor you're using. In my case, it's going to be a 64-bit Intel processor, so this is going to be the assembly code that the compiler will generate. After we have this assembly, then we will also assembly, or sometimes people also call this step compile, this language into some object binary. So now we're going to take all these assembly instructions, and then we're going to turn this into a binary format data that the computer can understand. And last but not least, we're going to link this program with some, for example, with the standard libraries or with some third-party libraries in order to get the final executable. So all these 4 steps, we can depict a picture like the one in the here on the slide, and then this is more or less all the 4 steps we're going to see. So first we have the pre-process step, so here, and then the output of this pre-process step is going to be the pre-process file, and then if we pass this to the compiler, then you get an assembly source file, and then if we assembly this assembly code, then we get the final binary file. And then the 4th and last step, that is going to be the linker, that this could also invoke some other third-party libraries, will give me the executable. So this sounds complicated, but actually you don't need to do this manually or to understand this manually every time you build a program. You only need to see it once, and that's why we put the lecture on the first place. And then once you get the intuition on how stuff is working, then you can really move forward and start using, for example, better tools like CMake, Make, and so on. So let's jump into this compilation process step by step, but checking what's going on. So for that, let me bring my terminal, and then let me clear the output. And then I am here, for example, on this directory where I will build a simple example. Let's remove everything. And now if I list the directory, it's completely empty. So let's start with a really simple Hello World program. So for that, let's include the IOStream header file. And then let's create our main function. And then let's call Hello World. And then no errors, so far so good. Now let's build this example. So this is how we did it on the first lecture. So now if we list the directory and then I execute this, it's going to give me the same example as before. But now let's really dive deep into all these 4 steps, and then let's see what we can do. So the first step, is going to be pre-process, and this typically will output a file that is not strictly necessary, but it's common to put a .i extension. So if I invoke my C++ compiler, like you see on the screen, this is going to give you the pre-process file on the standard output. So this is going to be on the output terminal, but of course we want to redirect this to a file so we can inspect it a bit. So let's do it. And as you see, we have a main.i file that we are going to open right away. So if you see now, this file is basically quite big, and there's a lot of stuff I didn't write myself. And this is basically everything that was copy-pasted from the IOStream header file. So the preprocessor went for this file, grab it, copy all its content, replace all the token strings, and put it here on my file. And if you pay even more attention, if you go to the bottom of the file, you will see my C++ program running here. But also, the include statement is not here anymore, because it got replaced with all the header file that we just got from IOStream. So this is basically how it looks, the main.i, that is a preprocess file after the preprocessing step. So this is, so far, you cannot use it, you cannot not run it. Therefore, we move to the next compilation step, that is going to be the compilation. So again, technically speaking, this is going to provide you with assembly code that you still cannot run, but you could turn it into binary objects. So for this, we need to pass the -s flag here, and then now we need to provide not the main.cpp file, but the preprocess file, because this is the one. So this is the second step on the compilation, so we need the output of the first step, right? So if we do this, now we have a third file that's going to be the assembly. So never do this, but you can open it and then try to understand the assembly code. So this is basically how it looks after the compilation process, first after preprocessing the file and then compiling it to assembly format. So this is basically ready to be turned into binary for this particular processor, and for this I will invoke the assembly. So for that, we need to call this and then do assembly this. And if I check now the output, I will have this main.o, that is going to be a binary format object file. If I try to open this file with my text editor, of course, I'm not going to see anything meaningful because it's all binary, and makes sense, of course. Then the last step, but not least, is basically linking, and to invoke the linking, which is go to the fourth and last step of the compilation process. We say, okay, let's link this main.o object file, and then by default we're going to link against the standard library of for example, GCC, that is the compiler we're using. And for example, here you will have the symbol to get through main and then to run your program successfully. So if you check now, so if you do this will give you an output, but let's put it into a file that we will call main. And this is basically the last step. And now we have our main executable. That is basically the final program. So this was basically all the 4 steps done by hand. Do you want to do this every time you build a program? Not really. So this is just an example to show you what's going on behind the scenes when you are using this. And if you want to know how I got to know all these 4 steps, you just do manual GCC. And if you check here, these are the 3 steps basically. And then there is also a really nice description on how this works. Basically, compilation can involve up to 4 stages: pre-processing, compilation, proper assembly, and linking. And here you have all the description on how to use these 4 commands, basically. So, if we recap, basically, if we want to compile a program, even when we don't know it, we're going to go through all these 4 steps. First, pre-processing, then compiling, then assembly to a binary, and lastly, linking. Of course, when we call the C++ main.cpp, all this is hidden from the user, and then we get at the output here the final executable. So now that you already know how to compile and you understand the 4 steps of the compilation process, we can dive deep into building libraries. Again, as a recommendation, before you continue with the video, I would recommend you to stop this video right now and try on your computer the 4 steps and play around with different type of file names, change some stuff on the C++ code, and to get some intuition on what's going on there. So what is a library? I like to think that the library is nothing but a bag or a collection of function implementations, let's call it. Later in this lecture, we're going to see other stuff like classes and so on, but for now, let's stick to functions or symbols. So when I say a bag, it's basically because inside this bag, if you open it, you will find different binary implementations. So this means stuff that your processor can execute and give you some output, all connected together or all packed together into one bag. Of course, because we are working on Linux and everything in Linux is a file, this library is going to be a file. So the libraries is basically, we can call this, that is multiple object files that are logically connected, but not necessarily. So you could probably have a library with some unlogical connection within this library, and there's no problem with that. And there's basically two types of libraries on the C++ world, or basically on any compiled language. One is going to be static library, that they are typically faster to run, but of course this takes a lot of space because they will become part of the final binary. And also we have dynamic libraries. Now we can say that they're somehow slower, but this can be copied to the target file system and then referenced later by the main program. I will explain a bit more about this in a second. So how to create a static library. So this is one command. We're going to see an example later. And then remember that static libraries are just like archives. So think this about like a bag of symbols. And now we need to make a full stop here, and then we are going to see this picture that it's very likely that you're going to see this again and again and again on my lectures. Why? Because it's really important to distinguish between the static world and the dynamic world on a C++ program. When I say static, I'm basically thinking, speaking, and trying to reason about everything that is happening at compile time. And this is always like this. So stick this to this concept, and believe me, you will get to understand a lot of stuff during the full course. So static for me is basically has the same meaning that compile time. And then dynamic is basically whatever is happening at runtime. So it's equivalent when I say dynamic to runtime. So whatever is happening when I start, so after I start running my program, then I will call this something dynamic. So if we go back to the previous slide, and then now we jump back into the static and dynamic libraries. So when we build a static library, and then when we link our program with this static library, this is going to happen at compile time. So when I build my program, when I hit make, the static library is going to be invoked and it's going to be part of my final binary. Therefore, we say that it's not that we say it's something that is happening. The binary file size is going to be bigger. And this for you might be not a problem, but believe me, if you are targeting mobile robots, for example, where you don't have infinite amount of space on the file system, this is not efficient. Especially if you have on your target system, let's say 10 or 15 different applications that's using the same library. If you statically link this library with your 15 applications, all your 15 binaries, they're going to hold a copy of the same library, making each binary really big, and maybe you cannot even put these files in your file system. On a desktop computer, on your laptop, this might not be a big problem. But believe me that for mobile robots, this will turn into a problem. On the other hand, the dynamic library, when we link a dynamic library with your program, this basically means that it's something that is going to happen after we start executing the program. So when we link, we basically put a promise to the program. We say, okay, there will be a reference on this file that must be located on the file system. And when we start running the program, when we start execution, every time we need something from this library, we are going to go for this file, open it, and then take the implementation of whatever function you're using from there. Therefore, you need to have the library on your file system when you're running the program, not when you're compiling it, right? This is the main distinction. Of course, if we go to the mobile robot example, where we had 15 applications, let's say, now these 15 applications, they're using the same library, but they're using also the same file in your file system. And this library, it's not anymore part of the final binary. And then we will reference this library, all these 15 applications, every time each application needs something from the library. So this is more or less the main distinction. And again, believe me, I'm going to repeat this picture many, many times because it's really important to reason about the static world and the dynamic world on C++ programs. So how we can start building our own libraries? So to do that, we need to start talking about the declaration and definition of functions, and then we're going to see functions on the next lecture. But for now, it's safe to assume that you all understand what is a function on a program. And then also we are going to extend this declaration and definition when we start seeing classes on the future. So a function declaration can be separated from its implementation detail. So this is how it looks on C++, a function declaration. So we say that it sets up an interface because it's basically going to show the input parameters of the function, what is the return value, the return type of the function, and whatsoever. But so far, we have no clue of what this function is doing. We know that it's void, so it's basically not going to return anything. The name of the function is called funcName in this example. And also it's going to take one integer parameter, but we have no clue so far what this is doing. But this is basically the input-output perspective, so the interface of this function. This is the declaration, and I also like to think this as a promise for the compiler. So when you see a declaration of a function, it's basically a promise for the compiler that someone will provide the implementation for this function. And the implementation or the definition basically holds all the source code, the real meat of the function on its body. So basically here what we see is again the same prototype, so basically the same interface of the function, but here with the implementation details. So we are basically printing some messages to the standard output. So not much fun so far, but it's a simple example to keep going. So this is the main difference between declaration and definition. So how we can start building libraries with this? So now we understand the distinction between what is the declaration of a function and its definition or its implementation. So in order to build libraries, we will want to basically split the function declaration on header files, and the implementation is going to be on CPP files. Why is this? Because when we want to use something from our own libraries or from someone else, we only need, when we develop the code, we only want to know the interface of the function. So in this case, if I want to, let's say that we can safely ignore the implementation for a moment, and then the only thing I want to know when I'm using this library is the prototype. So which type you're returning, which arguments do you take? And that's why we want the header file. We only want the high-level description of the function. And this tools.hpp, this is the header file where we're going to put the function declaration. So there will be no source code in here, and this is the only file we need when we pre-process and compile the program to say, okay, we include this tools HPP, that is basically copy-pasting the header file into this program.cpp, and then we are going to call this function. So basically, this is the function, the call for from this library. And then later, we need to provide the implementation for this function, and the linker is going to be in charge of getting this implementation when we build it. So this is basically how we typically split the definition or the implementation and the declaration. So in this case, I call these tools because let's pretend that there was some tools in here. And here we have the header file, and here the .cpp file with the real source code. And this is the main application or the target application that is going to use the functions from this library. But then, can we just build as before? So we say C++ program CPP, actually no, and then we're going to get a link error. But in order to show you this, and then so you can believe me, let's build an example on the fly. So let me then open a terminal here, and let's start baking this project from scratch. So let's go to a temp directory, and then let's create example project, or let's call this my library, and then let's cd into this library, and then that's where we are right now. And to start, let me go back to the slide, and let's do these three functions, sorry, these three files, let's create it and then let's put some implementation in there. So, sorry, let's go back to my terminal, and then to create files, let's just use the touch command, HPP, and then let's call it main for the program .cpp. So if I list here, this is what I have so far, and not too exciting. So let's open an instance of VS Code here so we can put some code. And then after we open this, let's exit the terminal because I'm not going to use it anymore. So, okay, so this is more or less my workspace. Let's put it simple. Let's open the header file here that is completely empty. Let's put the main application to the right. And then let's put the CPP file over here. So that's it. So this is more or less how I like to have it right now. So this is our workspace, and let's build first the header file, then the CPP file, and the main application. So let's get started. So let's say here that we want to have some function that is called greet, and then takes no arguments, and then that's going to be basically the function declaration. So this is a greet function that looks to basically greet someone or something, and then takes no argument, and basically it's a subroutine, so it's not doing anything. Of course, you can help the reader provide some comments, and this is a function that will greet you. And then so far, so good. Then on the implementation, on the definition of the function, let's include the tools.app file, and here we are going to provide the real implementation, the real C++ code for this function. So then let's repeat the prototype of the function, but now we open the scope operator because we're going to put here the implementation. So in order to output something to the terminal, we're going to use the iostream header file, and then here we just do cout, and then I love build systems, for example. And this is just a function. So let's put some comment here, like say how much you love to build C++ programs, right? And then now there is a caveat. So when we include this file, we are going to copy paste whatever is on the header file on this other file. But if we jump to the main program, we also need to include the tools.hpp file in order to use this function, the greet function. But the promise is when we compile the full program, we're going to get twice this function declaration, and this is basically a syntax error. So in order to do so, to fix this error, that actually is a nice exercise, you could try it, and then you will see on which of the 4 steps that you should probably know in which one is going to fail. This is going to give you an error. In order to avoid this error, we're going to specify the preprocessor to only include this file once. So pragma once. This basically tells the preprocessor the first time you see this file, copy whatever it should be, and then stop there. Otherwise, we will get twice. It's like the same as having this 2 or 3 times here, that this is going to give you a syntax error. Okay, so far so good. This is more or less the basics you need in order to build this library. Now on the main program, we are going to create a main function, and then let's invoke this function. And then this doesn't look to be the, let's also return 0 here. Doesn't look to be the big thing, but believe me, it's a lot, because we have a library here on the left, and basically we have a main program or main application calling a function from the library. So maybe you want to already go ahead and try to build this example as before. So let me list the work directory. So we have our main application and the library files. But if you do C++ main.cpp, you are going to have an error. So that is the same or very similar to what I put on the slide. What is saying here is basically undefined reference to the greet function. And why is this? Because the linking process is the part that is failing. So the 4th step of the full build or the compilation process is failing. And actually you can also, so LD is basically the GCC linker. This will also give you a hint or which step is failing. So basically you cannot tell that this is not compiling, so to say. You could say that it's not building, but actually the problem, so it is compiling, but it's not linking. So if you go to the 4 steps, the last step is the one that is missing. So basically then the question is like, what is linking? So basically linking is when the library is a binary object that contains some compiled implementation of some method, and linking will map function declaration to the compiled implementation. So basically if we go to our source code, so this function declaration needs to have a real reference to this implementation. And if you actually pay attention, we didn't compile this translation unit, this tool CPP, so no one knows where is the implementation for this particular function. So to use the library, we need always a header file that also we call it the API. That is basically where the function declaration it is, and also the compile library. So now we need to compile the library. So how to build the library? So here is basically, again, I'm repeating the example I'm building on the VS Code. So basically we have our folder with the tools header file, the CPP file, and then in short we will separate the code into modules. And then basically this is the full implementation, so you can also stop the video and try it by yourself. But now we are going to build this library by hand. So this looks like a lot of commands, and they are. So there are 4 commands in order to build such a simple library that you may think already this is an overkill, and I agree with you, but stick with me, because the more you understand these 4 steps, the more you understand the linking process, the compilation and the assembly, the more you're going to be able to debug your build when it's not really working. So the first thing we're going to do is to build a library. So no one built the library, and this is basically the first 2 steps over here. So let me highlight it for you. So these first 2 steps is basically going to give you the library of this tools library. So let's, without further ado, let's just do it. So basically, again, empty, let me jump here, empty directory, and then let's basically do C++, and then the -C flag stands for compiling, and then let's compile the tools.cpp, and then basically this will give you this binary object file that is already pre-processed and compiled. So pre-processed, assembled, and compiled version of the library tools that inside here there is only one symbol, that is the grid function. So now we want to organize these modules into a library, and for that we're going to use the archive program that is IAR, and then basically this is going to give you this libtools library, and then we're going to do this for this example as a static library. So let's do it. So basically if we do R and then we pass these arguments, this is going to be the name of the library, and it's really important you always start with the prefix lib, otherwise this is not going to work, and I'm going to show you why later. And then here let's put all the object files that we need for this library. So in this case we only have this tools.o, so it's only one module, and let's pretend we have more and more, so we can put it here, all the object files we want to zip, we want to gather together in this bag that we call a library. And if we list now we see this libtools, that is basically the static library we just built with just one symbol, that is the grid symbol. Now that we have the library, we need to compile, that is the same step we did for the library translation unit, the tools.cpp. We need to compile our main application. This will give us another object file that is going to be related to the main application. And lastly, the 4th step of the compilation process, we need to link everything together. In order to do so, we're going to call again our compiler, and we're going to say, please link this main.o object, and then with the libtools library, and we're going to output this to a main function. So let's do this on the terminal right away. So let me clear here, and then let's call the compiler for the main.cpp file, And now we have this new object file here that is going to have the binary code for this, and it's going to have the reference for the static library. So we need to link it, otherwise we're not going to be able to run it, because that's what we had before, an undefined reference to the grid function. Then if you go back to the slide, you can stop the slide or write down this command. Basically, we're going to call the C++ compiler again, and basically skipping the standard because we are not really using anything from the C++ 17. But if you put this, it's not going to make any difference. And then this -l with the capital letter is going to indicate the linker, please look for libraries on this current directory. And this -l tools is basically telling the linker, link against the libtop libraries, and that's why we always prefix a library with the lib. And then lastly, the -o, we already used it in the past, is to get some output file that we're going to call it the main. So basically, let me check my cheat set again. So main.o -l basically is please link with libraries on this directory, because the libtop libraries, it's on this directory, but if you have it somewhere else on your system, then this you will need to change. And then let's link again the libtools library, and then let's output this into a main file that is called main, and this is going to be the executable. If you list now, finally we have our main application. And then let's clear the screen, and then let's try to run this. And I love build systems. So as a recap, look all the files that you have right now, and look how simple this library looks. Even when it's simple, it's actually really hard to build, because there's a lot of steps involved in order to get there. But at least we reach this headers and source separation. We have on the left here our library code, and on the right we have the target application, that is the main application, that is a clean implementation of this library. So that's what put us into the final state to introduce you with build systems. So building by hand, it's actually really hard if you think about it. So 4 commands to build such a simple hello world example with just 2 symbols or maybe 1, it's way too much. Of course, if you think that you want to change, for example, this implementation, then you need to build this translation unit, then you need to recompile the library, you need to archive this into a library, then relink again, and then you will get the new target application, which is a lot of effort, as you can already imagine. So the question is like, how does this scale to big projects? So how we're going to deal with this when we have more than 2 files or a bigger library? So this, of course, is impossible to maintain, and therefore humans have created build systems. So build system to the rescue, and then let's dive into this. Let's do an example, and then you will have all the tools necessary to build your projects during this C++ course. So you may be wondering, what are build systems? So they are basically tools, and then you should not get lost with it. So the concepts never change, and that's why we provide you first with the intuition on what's going on behind the build process, but the tools might change in the future. So don't get lost with picking build system, because it's just a tool that might change. The important thing is you need to understand what is the build system doing for you. There's many of them nowadays, of course, because people have been doing this for years already. And the main idea of a build system is to automate this build process we just did by hand. Of course, somehow we really need to do this on an automated way, so we can change something and really easily rebuild the project. They began as shell scripts in the past. Of course, you may wonder, okay, 4 commands, maybe I can put some parameters, write a bash script or a shell script, and then I will have my build system. Of course, this is doable, but again, as you might imagine, it's really hard to maintain. Then they turn into something that is Makefile. So Makefile is basically the first open source build system out there. Was created in the GNU project, the same that created GCC. But then they also turn into meta build systems like CMake, that is nowadays the most popular tool used out there. So why we call it meta build system? Because the tool like CMake is going to give you a build system that will allow you to build your project. So accept it, CMake is not a build system, it's just a build system generator. So it's not a real build system. You need to use an actual build system like Make or Ninja in order to build your project. So this is basically something I wish at this moment. So let's pretend we never saw CMake, we don't know anything about Make. This is what I would like to do, basically. So I'm dreaming at this point in time. So basically, I would love to replace this. Let's highlight it with yellow. The first command, that this will give me the tools.o file, and the second command that is going to give me the final library archive, which is something like this. So I would love to have some build recipe where I say please add library and create it with this name. It's called tools, and then the translation units that will be part of this library are tools.cpp, and could be much more, but in this case we'll have one file. So this is something, again, I'm wishing that someone gives me this tool, because that will make me really happy. Then we have the third step that is going to give me some executable file, and then actually it's basically these two steps are also combined somehow, but let's say that we want to add some executable. That is, we want to call it main because that was the name of the example, and then for this we need the main.cpp translation unit, but again it could be more. And then lastly but not least, I also want to link these two modules together with this command, that is the for command we just ran. And then for this, I would love to have something like, okay, please link this main target with the tools library. And then luckily, so you're in luck, this actually exists, and this is real CMake code. So basically you can automate this 4 lines of shell script with a really simple recipe for CMake. So CMake will simplify your build. So it's one of the most popular build tools out there. Does not build your code. So keep in mind that you will always need to do 2 steps. When you run CMake, first you are going to generate the build system, and then you're going to build it. So it's always 2 steps, and then keep this in mind. It's cross-platform, so you can also use it on Windows, on Mac OS. You can target different architectures and whatsoever. And it's very powerful, but still the build recipe is really readable. So make files were great, but when the project gets bigger and bigger and bigger, the make file is actually turning into something that is really hard to maintain and to read. So how we can build CMake? So in order to do so, let's first turn our library project into a CMake project as an example, and then we are going to go back to the slides. Okay, so we are back with our text editor. First, let's clean up a bit the workspace. Let's remove everything. This actually we can use the globe you just learned from the last tutorial, and then this will give me main, and then this will give me only the source files I need to create the project. So in order to create a CMake project, we need to provide the CMake list recipe, and then for this we are going to create this file over here. And now if you see, let me basically close everything and just stick with the CMake list file that is of course empty because we just created. So the first thing we need to specify to CMake is the CMake minimum version. This is somehow mandatory, so we need to provide it. And then let's put version 3.1 just because. And then we need to specify the project. And then, for example, my library is going to be the project name so far. And then, for example, we can put the standard, like say in C++17, but let's keep it for now, because we are not really going to use anything from C++17, so we can safely skip. And then one thing we could do with CMake, for example, is to include directories, and then this will specify CMake where to look for header files. In this case, the header file is basically here on dot, so on this particular directory, so this will be enough for now. And now let's try to remember what we did with the manual build, and let's try to code it with CMake. So the first thing we did is to build the library. Then we say add library, and then we call this library tools. So here's the name of the library, and for now we only use this tool CPP file that is here on my workspace, right? The tools.cpp file. Then we need to add the executable, and this we call it main, just because we wanted to call it like this. And then we need this main.cpp translation unit. And the last step was to link these two guys together. And for this we use target link libraries. And then we call, let's link the main application with the libtools library. And then something I like to do with CMake is to set this variable that is CMake export compiles command. That this will give you a JSON file we're just about to see to inspect somehow what's going on. Okay, so far so good. How we build this project with CMake? The first thing we need to do, let me put this here, is create a build directory. And build is just the name. You can put whatever name you like here. Most of the people will be using build. So put the name you prefer, but it's actually the same. Now let's go into this build directory. And then now we need to invoke CMake. So CMake needs to know where do you have your CMake list file, and in this case it's going to be ... but it's going to be here on this directory. So we just do CMake ... and if you see, now CMake just run with the recipe we just provided, and there's some information, but for example, let's check this one that it says the C++ compiler is GNU, so it's GCC, version 9 and whatsoever. Some more information, but not too much we care so far. But as you might know, because we just said it, we didn't build the project so far. So CMake, after running, gave us a build system. So now, by default, if you don't specify anything, it's going to be make. But in this case, it's make. So if you check this build directory, you will see this make file that here is basically the build system. So now we are ready to make our project. So if you just hit make, you will see all this output, and then without doing anything, we just did all the 4 steps we just did before manually, but through the build system. So how cool is that? And actually, now that you understand how everything works, you can read this and understand it, and it's not going to be black magic for you. So building C++ object tools.cpp.o. So this was the first command we did when we did manual stuff. Linking C++ static library libtools. So this is when we invoked the archive command, and then basically we created the archive, the static library. Then we finish with the target tools. This is just a debug message. Then building C++ object main blah blah blah. This is basically the third command we did. And last but not least, linking the executable main with the libtools library. And as you might expect, here we have the libtools library and also a main application that if we run it, we just have the same output as before. So how cool is that? How simple it is to use this build system. And actually, let's open the compiles command.json on my text editor. And if you inspect somehow this, you will see that you have 2 commands that is basically the compilation commands that they look really similar to what we just did manually. So we invoke C++. This is going to tell where to look for header files, so -i, and then it's going to output the binary object module, and this is going to be the CPP file. So this is one way to know what is the build system doing. Other thing you could do, let me remove everything so we clean. And then let's remove this, sorry. Now it's clean. Now we rerun CMake, and instead of doing make, we're going to specify make to be super verbose. So verbose equals to 1, and then we run make. And then this, I recommend you to do it in your computer, but if you inspect now all the intermediate steps, so this is going to be really similar, but with some other stuff, to what we just did when we were building the project by hand. So this is not super important, you can just do make, but in case you want to go more deep into what's the build system doing, you can just do verbose and check what it's doing. So actually, in our case, we do not need these two stuff, so these two lines. So our build recipe is basically the 3 lines we wished before to have, and then I'm happy we have a tool like CMake to simplify the build process for us. So now let's jump back into the slide. So as you see, the build process from the user perspective is very simple. First, you go into your project folder. In this case was my library folder. Then you need to create a build directory. Then you need to go into this build directory, run CMake, and then make. Make is going to build the real project. The step number 4 is going to give you a build system. The build process is completely defined in CMake list.txt and children file, so you can also put more CMake list file inside each directory on your project to simplify somehow the build process. Sorry, not the build process, but the build system development. And actually, this is something that is useful because one way that I always do, and I also recommend you to do, to get to know a project is through its build system. So by understanding how people is building their projects, you can also get to understand, and you will get the chance to get the intuition of what's going on that project by just knowing what the build system is doing, which is rather nice. So here we have something really similar to what we just did. So again, if you're watching this video, please stop it, go to your text editor and try to reproduce what I just did, and also try to play around with the names to see how you can break it and whatsoever. The only thing we didn't do is to take the CMake standard because we are not using anything from C++17, but for the sake of completeness, I put it here for the slides. So you should basically always have it there just in case, because in the future we're going to see C++17 related stuff. This is more or less how a typical project structure will look. So you're not forced to follow this project structure, but it's somehow how I like to organize my code most of the times when I'm writing C++ projects. So we have the build directory, the result directory with some binary and lib library files. They include a directory where all the header files will lie, the source directory, the test directory, and whatsoever. So this is more or less, if you want to start a project from scratch, this is probably a good starting point, just as a structure. So without thinking on what thing you will put in which file, basically. So the compilations options in CMake again are rather simple. So instead of specifying the flags for the compiler, you can specify on the build script. So this is not so relevant so far, so I will just leave this slide for you to read in the future. And then lastly but not least, so there's some CMake stuff you should know. So I'm not an expert in CMake, and I guess you should also, there's no need for you to become an expert, but the more you know about CMake, the easier it's going to be for you to develop your build system. So CMake is just a scripting language like Python and other languages. So of course it has features of a scripting language like functions, control structure, variables, and whatsoever. And then something really important in CMake is that all variables are strings. So keep this in mind. If you want to set some variable, you can use the set value, and then you specify the variable, and then you specify the value for that variable. If you want to get, for example, to print to the standard output which value is on this variable, you need to use this syntax. And then if you want to somehow provide some message to the user, you call the message function with the message, which is also a string. And of course you can have warnings, errors, so if you don't have some library, stop the CMake process there and whatsoever. So this is more or less like a summary of 3-4 stuff you should know for CMake, but believe me, stick to the lectures, continue with your homeworks, and then you will get used without much effort. So this is basically how you build project with CMake. So just cd, CMake, and make. So you will always repeat this. And then lastly, for making these projects, so keep in mind that if something goes wrong, it's actually really easy to start over. Because before, remember that when we did the build process by hand, we have all the files there on our working directory, and it was a bit messy to remove all the files we didn't. We wanted to regenerate to make sure we have a clean build from scratch. If we want to do this with CMake, it's rather simple. We just go to our terminal, and then we just completely wipe out, completely remove the build directory, And now we have our clean project again, and then we can rerun basically the whole process. So we go to build, we just run CMake, and then we just build our project again, and then it's working. So maybe sometimes when stuff is not working, it's a good idea to just remove the build directory and start from scratch when something is really not working. So find package is basically probably the command you will use if you need, for example, to use some third-party library like OpenCV. So in this case, we are not going to see right away how to use third-party libraries, because for the first 3 or 4 lectures you're not going to need it, and also for the homework. But this slide here is basically for future reference for you when you need to go and find packages for OpenCV and other libraries. So for the homework, I highly recommend this video on YouTube. So it's 100 seconds introduction for Git. So Git, again, is part of the software development environment or ecosystem that you need to use in order to write source code. And then these are basically the reference. So all the information I took from the GCC manual. It's big, long, but if you have some time, it's also a good idea to read to make sure you understand all the details of the compilation process. So that's basically it. Thank you very much for your attention. And again, get used to build systems. They are great tools that will allow you to build your C++ programs, and then will allow you to move forward into this learning journey. I hope you enjoyed the lecture, and then let's see you on the next one. Thank you very much for your attention.